Hi everybody, good morning. Welcome to JuliaCon 2017 and to this morning's first workshop, which is going to be basically an introduction to Julia 0.6 and the future of Julia. So the materials for this workshop are available at this GitHub page. My GitHub page, github.com/dpsanders/Julia_towards with an S because I'm English _1.0. And so there you can find the materials, which are Jupyter notebooks, which I'll talk about in a minute. So you can just read them right on GitHub by just clicking on them, or you can download them and open them in your Jupyter notebook, and there are various other ways you can use them. Can you see that? So I work at the Department of Physics, the Faculty of Sciences in the National University of Mexico in Mexico City. And I've been using Julia for about 3.5 years, since actually I basically learned about it at Berkeley from Jeff Bezanson, one of the creators. So what is Julia and why are we all here? I think you probably know that it's a programming language. And it's a programming language that's been designed from the get-go, from the start, to be take the best out of most other languages out there. So it has ideas from Lisp, Ruby, Python, C, Fortran, I mean, from everywhere. Take the best, get rid of the worst, and think about how to design a programming language for today. So what do I need from a programming language? I need it to be interactive. I want to be able to ask Julia what's going on with my data or my code in an interactive way. That's why Python became so successful and MATLAB. But at the same time, I want, great performance, which is why C and Fortran are still used. And so Julia really is one of the only solutions that provides the best of those two worlds, because it's interactive but also compiled. And so it can be fast. It can also be slow if you don't use it correctly, but the point is that if you start off with some slow code, it's usually relatively easy to make it fast just by tweaking a few things, whereas in other languages, that's not the case. And Julia is extensible, so in every language I can just write a load of libraries, but the point about Julia is that I'm going to write those libraries straight in Julia, and it's going to be performant. I don't have to change to any other language to do that. And so that leads to the fact that there's a whole ecosystem of getting close to 1,500 packages now, which are designed, or maybe not even designed, but they interact very well with each other, just because of the way Julia is designed more than anything else. And we'll see a bit of that later. So that's what we call composability. So I can take one package and stick something from another package into that first package and have them work very well together pretty easily. So to summarize, Julia allows me to write code that is readable, but it's also generic, which means that it works with objects of different types, and at the same time it's fast. So this seems to almost be like a pipe dream, and that it can't possibly be true, but that's one of the amazing things about Julia. So you probably know that literally yesterday afternoon, version 0.6 of Julia was finally released. So that is now the stable version, and the stable version of the Julia docs refer to now the 0.6 release, and sometime soon there will be, I don't want to commit to when, there will be a 1.0 release, which will be the first long-term stable release that you can really rely on to not change under you the basic syntax of basic Julia objects. So how are we going to use Julia? There are several ways, quite a lot of ways now that we can use Julia. So we can do it from the command line, or the REPL, the read eval print loop. So it says so from the terminal basically, which we can use for interactive experiments, and there'll be a talk about how to customize that REPL experience later in the Oh My REPL talk. We can use the Jupyter Notebook, which is what I'll be using, which enable me to make coherent narrative documents that include equations, figures, code, all in the same place. And Fernando Perez's keynote will be about that. There's a desktop app for using Jupyter Notebooks called Interact, without the I. And that's pretty neat. Then one of the main efforts in the Julia community has gone into Juno, which is a Julia Integrated Development Environment, or IDE, which is written based on, or sort of inside the Atom editor. And that enables me, for example, to have the usual things, syntax highlighting, but etc. But it also has inline evaluation, so I can evaluate Julia code right in Juno. I can use Julia Online at juliabox.com, which is an online Jupyter Notebook server. And then Julia Computing has this Julia Pro version of Julia, which is the basic language plus a whole load of packages that are guaranteed to work together, and they support that professionally. So if you want to follow along, you'll need to install the Jupyter Notebook. So you need to download the version 0.6 of Julia from the homepage, the Julia Lang homepage, and then you need to run Julia and follow these commands. Package add iJulia, that will install this iJulia package. Be careful that it has a capital I and a capital J. That's only once in your life that you have to do that, or once in each Julia installation. And then it's a bit difficult to read this, but it says using iJulia, which is going to load the package in each time in each session, and Notebook, which will run this Jupyter Notebook. And whenever we're working in Julia, we can use the pwd command, print working directory, to tell us where we're actually working. Now, it's kind of difficult to get started with any new programming language, so we're going to need some help. So Julia itself can provide lots of help. For example, I just type $sin or sign in any kind of environment that's interactive, and it will give me inline help for that command. We'll see that a bit later. There's a very extensive Julia manual that I've linked here under Julia Docs. Of course, Google is your friend. And then, if none of those work out, there's the main online sort of help support network forum is this Discourse. That's the name of the software that runs the site, Discourse. Discussion forum at discourse.julialang.org. And the community is very friendly, and people will be very happy to help you, as long as it's clear that you've already kind of tried and failed on your own first. And then there's a chat room for actual chatting, sort of quick and easy questions on Gitter. Also, since we're at JuliaCon, hopefully you all know by now that there's a JuliaCon Slack. That's another chat service. And you can use that. So there's different channels for each of the rooms that are set up so that you can discuss things as they're going on in real time. So what is this tutorial about? It is an introduction, but at the same time it has some more advanced things in it. I'll try and emphasize how I personally kind of go about using Julia, what kind of workflow we might use. There'll be some aspects of today's Julia 0.6, so a lot of the things that I'll talk about won't work in 0.5 because they're new in 0.6, which is part of the point of the tutorial. I'll mention some key packages, so many of the things that we'll use every day are not actually in so-called base Julia, the standard library. They're actually out in separate packages, and so I'll mention some of the ones that are useful. And I'll try and minimize repetition from previous tutorials, in particular my previous tutorials. So I do suggest that if there are some things that are not clear, you can always go and look at some previous tutorials. Just bear in mind that some of the syntax does change between different Julia versions. So we have a help, an assistant with us today, Sasha. So if you have any questions, just stick up your hand and he'll come over and help you. Unfortunately, since we have so little time today, I'm used to tutorials that are twice this long, so we have 2 hours, so I'll just go at quite a fast pace, but do, of course, feel free to ask questions, but I won't be able to go and help out with things. So, any questions? So I won't go into more of the philosophy behind Julia, really. That's been covered in a lot of other places, probably better than I can do it, so we'll just get down straight to nitty-gritty. So there are basically 4 notebooks that I hope to cover today. So we'll have a basic syntax and workflow on one particular problem that I like, so with a worked example on random walks. Then we'll look at some arrays that have changed a bit recently, and a key point of Julia, which is types and this thing called multiple dispatch, and then metaprogramming, which is another really big subject. So I'll try and stick to half an hour for each of those. Please let me know when I'm running over time. So I've already lost 15 minutes, so yeah. Okay, let's get started. And I should, of course, have removed all the output from all the cells. I forgot to do that. I always forget to do that. Okay, so let's just jump straight into some Julia code. This is going to simulate a random walk. So what's a random walk? If you don't know, it's just a particle that's jumping left or right on a line at random. So why do I care about this? Because it's a key model in biology, physics, and chemistry of a molecule moving in a fluid, for example. And so we'll see an animation of it in a moment in case you don't know what I'm talking about. So here's a nice typical piece of Julia code. So it's just this block in the Jupyter notebook, and I can edit the code in that notebook. And so I'm defining a function. So everything in Julia is always going to be inside a function, because that enables us to reuse the code, of course, but also in Julia it turns out to be key to having good performance, that everything should be in a function. So let's define a function. It's going to be called walk, and it takes one parameter called t, which is the maximum time of the walk, right? So upstairs, just before the function, I've written a doc string. So this is a string. So we write strings with quotes, double quotes. And if we use 3 double quotes, it's going to be a multi-line string. And then this is going to be the documentation for this function. So once I evaluate this cell, which I'll talk about more, the code more in a minute, I can then put question mark walk, and it'll give me the documentation for this function that I just wrote. So here's the documentation, and we can see that, you can hopefully see that it uses different fonts when I put these back quotes, because I'm using actually markdown syntax inside the doc string. So I'm defining a function walk. It takes this parameter t, and it's going to start off with it's going to have a position x, which starts at 0, and it's going to change every step when I jump randomly. So to jump randomly, I'm going to use an if. So I'm generating a random number with rand. So rand is a function. If I just type rand, it'll tell me that it's a function. And if I call it with empty parentheses, then it will return a random number. And I can repeat this cell, repeat evaluating this cell with control enter. And I can see that indeed it's spitting out some random numbers, uniformly generated between 0 and 1, uniformly distributed between 0 and 1. So if that is less than 0.5, then that's an event with probability of half. So with probability of half, I'll jump to the left, so to the right. So I'm changing x. I'm modifying x by adding 1 to it. Right? So if x starts out at 0, and then Julia will tell me that it's 0, and then I add 1 to it with this command, then now x is 1. And that's the same as writing x equals x plus 1. And so, so I jump to the right or I jump to the left if that's not true. And then I'm going to store the trajectory of this walk so that I can plot it. So I'm going to store it in a vector. So that's what this line does. It initializes a vector. Right? So if I have this value of x and I put trajectory equals the vector, so with there's a square brackets there with just x inside, that will make a length 1 vector, so which is a kind of array with 1 dimension, and it stores integers inside, and it just has 1 of them. And then the next thing I'm going to do is use this push bang function. This is this exclamation mark is a convention in Julia that it's a function that modifies its argument. So I have this trajectory object which is going to be modified when I add for example, x plus 1 to it. And so that added an element to the array. And then at the end of this, so I have a for loop with this 1 colon t syntax. So what's that? So 1 colon 10, for example. So if I call that r for range, then the type of that object is a thing called a unit range. So basically it acts like a vector, but it doesn't store explicitly the components of the vector. So it's a kind of generator. So that's the whole function, and at the end it's going to return this trajectory that we just calculated. Questions about that? So I'm presuming that everybody has some programming experience. I'm not going to talk about what a for loop is, and but do ask questions. So here's an example trajectory. Let's make it a bit longer, and then we'll use show just so that I don't waste so much vertical space. So for example, walk 100, there is a random walk going on, and indeed it returned something. So if I call traj that thing, then what is traj? Sorry, I don't want the show there. I can put a semicolon to hide the output. Then there's the output. So now I can do show of that. So show just displays the thing in a slightly different way. In this case, it doesn't display it vertically, this vector. And that object is, again, this one-dimensional array. So we've already written the sort of world's simplest interesting simulation, a random walk. So now, what do I want to do with that? So the first thing I would think of doing is visualize it. So there are lots of graphics packages in Julia, but there's one that has sort of taken over a lot of the field, which is called plots.jl, and it has taken over because it's basically a sort of a higher level package that actually has a unique syntax which is able to feed in the same commands to all these different packages with their own syntax, basically. And so so to add this package, if you don't have it installed, you would do package add plots. That's just, again, once in your life. And then every time in every session, in every new Julia notebook, or in every new terminal, you'd need to do using plots to actually load the package in. And then I'm going to be using something called the GR backend. GR is the name of a graphics package that you can use from various languages. And there's a Julia interface, gr.jl, the Julia package that interfaces to that C code. And then this little gr function actually is going to load the interface between plots.jl and gr, so what's called the backend. So then, so all this plotting is code that's from the plots.jl library, and I can actually just load up any other backend and plot with another backend. So, so there's a lot of annoying details in any plotting library. I won't talk about the details, but they're all in the code, so you can just basically copy and paste the code. So, so for example, so I'm going to plot some lines, and let's add some markers. So this m equals is a keyword argument, and I can also write marker equals colon square. So things beginning with colon are something called symbols in Julia. It's kind of like a special type of string. So the basic command is plot, and I give it two vectors, one which is the x coordinates and one which is the y coordinates, just like in most plotting packages. Then all of these functions that have bangs or exclamation marks at the end are going to modify the plot. So here I'm going to add a horizontal line. And so there we go, there's a nice random walk plotted using gr. And now let's change, and this is probably a bad idea because I didn't try it out. We're going to use a different backend called plotly.js. So this pink box here, which has a warning in, basically that's because 0.6, Julia 0.6 is so new, some of the packages have not yet been updated completely to the correct new syntax. So that's what all these warnings are. So deprecation means a syntax that has changed. So it's actually warning me that I'm using the old syntax. It's not an error. I can still use the old syntax for one release of Julia. So yeah, sorry, I should have done that before. So the first time you use any package in Julia, or you update you update a package, it will recompile the package, and that might take a long time, but then the next time you use it will be fast. Okay, so I'm going to actually just redo the same command with this new plotting library. So again, the first time you run a command, it'll compile a load of code. And there we go. This is now using the other plotting library, which has the benefit of being interactive. So I can, for example, zoom in a piece of the thing, and then zoom out again. And the point is, it's exactly the same code, and I can run it on all these different backends, which all have their own pluses and minuses. Okay, so now let's draw a few walks. So here I'm doing a for loop. So I'm making an empty plot and then adding all of these different things, and then drawing my horizontal line, and I get this nice output. I'm going to switch back to GR because I'm about to draw a lot of lines, and GR is usually the best for drawing a lot of things at the same time. So a few hours ago, like 5 or 6 in this morning, Shashi, who's one of the Julia computing developers, patched an important package called interact.jl. Well, actually, he patched iJulia, this interface with the notebook, so that interact would work. So you need to check if you've already previously installed iJulia, you can check which version you have with this package.status command, and you'll need 1.5.1 for the following thing to work. If you don't have a recent enough one, you can update all your packages with package.update. You should definitely go to the package 3 talk. I can't remember when it is, maybe tomorrow, which is about the next version of the package manager, when all of what I'm saying about packages will presumably become obsolete. So we're going to use this interact package, because what I would like to do is, okay, this picture is very nice, but I actually want to make it interactive. So Alan Edelman, who's one of the founders of Julia, always says that everything is better when it's interactive. So everything is better with this @manipulate command. So what does the @manipulate command do? It provides me some sliders that come from, currently at least, come from the Jupyter Notebook, but I believe that's going to change if you go to the webio.jl talk. And I can slide these, and then the graph will interactively update. That's really pretty cool. And so how does it work? So I basically have the same plot command that I had before, but I just wrap it in this for loop. And it's a special for loop. So Julia allows for loops to have more than one clause, so more than one variable that's being looped, right? So here I've got t that's looping from 1 to this max t, and n that's looping from 1 to max n. So basically this is just a simple syntax for two nested for loops. So I've got these constants outside. And so if I take out the manipulate, it will just do one of these plots after another. But when I add this manipulate in, it will sort of somehow magically turn this dual for loop into this interactive plot. So that magic that's happening, I'll talk about at the end of the session today. That's a macro that's actually taking this code and manipulating it in some way and making some more complicated code to do this manipulation. Okay, so now I've got a feel, going back to my workflow idea, now I have a feel for what the system looks like, what it's doing. I want to actually calculate something. So let's do some data analysis. So one of the things I won't talk about today is the Julia's ecosystem for data manipulation, mainly because I don't know anything about it. And but there is an ecosystem which is kind of undergoing a lot of change at the moment. Data frames and data tables and streams and things. So hopefully there'll be various talks about that you can go to. Or otherwise, just ask people who work on that. Okay. So I want to calculate, for example, the variance of the final positions of these walks. So I'm going to rewrite my walk function to not any longer store the trajectory. I'll just return the final value. Right, so this is the final position that it's returning. And now I'm going to make a function called walks, which takes an n, which is the number of walks, and t, which is the final time, and does the standard variance calculation. And I'm going to run this code with 100,000 walks up to time 10,000. And that takes 2.5 seconds. And then I'm going to run it again, exactly the same command, and it now takes almost the same time. But what's interesting is that the number of allocations, so how much memory this thing used, went down basically to 0. So this should not be allocating any memory, this code. There's no arrays being created, there's nothing happening. So it shouldn't be allocating any memory, whereas the first time it allocated a lot. And that's because the first time it was compiling this function. So basically, when we're sort of timing things, we should always discard the first time we run a piece of code. And this @time sort of super function, @time macro, it just takes a piece of code, runs it, and times it. So how fast is this? Is this fast or is this slow? Right? So the claim is that Julia is fast. I wrote the simplest possible for loop, which in C, would be fast. In Python or MATLAB, it would be slow. And the answer is that this is 2 and a bit times faster than my C++ code. So that probably, I included the C++ code, I think, in the repo. Please, if there are any C++ experts, please tell me why I'm able to run this twice as fast as C++, just with the same code. Julia's not that good usually, but maybe it's doing some clever vectorization under the hood that I don't know about, right? Okay, so that's one way of, we're always concerned we shouldn't always be concerned about performance. Performance is not always important, but in the end, one of the reasons for using Julia is because it has good performance, and so that's why there's a lot of emphasis on benchmarking and things around in the Julia community. And so just in terms of tooling, this @time is sort of a very it's a quick and an easy way of benchmarking something. It just calculates how much time it took to run the piece of code and how much memory allocation was going on. But it's not actually a very good idea to use it, especially if you're doing what's called micro benchmarks, which are these sort of really quick little things. You're trying to check, is it faster to run the built-in sine function, or is it faster to run my own sine function that I just built, for example? So for that, we should use this package called benchmark tools, which is a very nice package. So for example, if I just run 10 walks for 10 steps, it's going to be very quick. And so if I do an @time on that, it tells me that it's, this 0.00002. You can't really trust that number. So what the benchmarking package does is it has this @benchmark macro, which will run this piece of code a lot of times and do clever statistics on it and report what it found. So here, this piece of code apparently takes around 300 nanoseconds. And there's, if you just want sort of one time, you don't want to be confused by all the statistics, you can do this @btime, so that replaces the @time command and gives you exactly the same information, and sort of takes some average of, or whatever, of all of these different runs. Okay, so if we're thinking about doing some kind of performance comparison, we should probably write a few ways of doing these calculations. So up here, I did a very C-like thing. I initialized a variable. I did a for loop. I added something to another variable. And this is kind of painful to write all of that just to calculate a variance, right? I shouldn't have to do that. And so, that's why MATLAB became popular, because it gave you a way of writing these things in a much more quick and an easy to understand way. And so indeed Julia has all of these things. So for example, I can make an array comprehension. So this is a way of creating an array sort of with the loop. So it's equivalent to this make an empty vector and push all these things in, but it has this nice syntax. And it also has generators. So if I use parentheses instead of square brackets, then it doesn't actually calculate all of these things. It just provides me a generator which, when I iterate over it, will produce one after another. So it doesn't actually store them in memory. So that's going to be more efficient in general. So here's another way of writing a random walk. What do? I generate all of these random numbers, random jumps, just in the same way. But this is now a generator, and I'm going to sum over that generator. So that's going to give me the number of rightward steps. Right? So this rand less than 0.5 will give me trues and falses, which I'll treat as zeros and ones in this, inside this sum. And so the number of right steps is this sum. Then the number of left steps is all of the other steps, and the final position is one minus the other. So the details don't matter, and then I'm going to make this walks function. So before I had a walks function that they're called one particular function called walk. But if I want to make my code more generic, I want to be able to call lots of different kinds of functions that do a walk, right? So I've just made another one, walk2. So I'm going to make a different new version, a new method of this walks function, which takes a function as argument, as one of its arguments. So it's going to call that particular function with parameter t, and calculate the variance. So Julia has a keyword, has a function var, which calculates the variance of a vector-like object or an array-like object. And so it's going to calculate the variance of this generator thing. And so if I do that with the original walk function, again I take 2.5 seconds. If I do it with this new walk function, for some reason I go back to the C speed. So I really don't understand what's going on. If anybody can explain it, I'll be very happy. So this is about the same speed as C, the second one, and the first one is this super fast Julian version. Okay, so let's, just to show how flexible Julia is, let's do two other ways of calculating these random walks. So here I'm calculating a whole load of random booleans all at the same time. So if I do rand of bool is a type, right? A Boolean type, so it represents things that can be true or false. And so if I generate a random one of those, I get false, false, true, 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 false, etc. And if I do rand of that, comma 10, I'll get an array of 10 of those things. So here I'm generating an array of t random booleans, and I'm taking the sum of that, and I'm calling that walk 3. And so I'm going to see how long that one takes. And that takes about the same time as the original one. So that might give an idea of what's going on. And now I'm going to do something very special, which is this bitrand thing. So what is bitrand? It again gives me an array of trues and falses, but now they're treated as bits. So they're actually being stored. Each true and false only needs one bit. And so it's just storing the bits. And so, I can stick 64 bits in one integer. One 64-bit integer. And so that's what's going on here. I'm generating 10,000 bits. And so I actually need to generate 10,000 divided by 64 random integers to do that. And so this one is super, super fast. Right, so that's the fastest random walk simulation you've ever seen, probably. And so
input to RAM?
Sorry?
Did you consider using a step range as input to RAM? -1, :2, :1?
Sure, you can do that. Good question, yeah. Yeah, you could do rand -1 to 2 to 1. Yeah, let's do that. Can you guess whether it'll be faster or slower?
Slower.
Yeah. Is that right? It should be walk 5.
Well, here you don't need right steps and left steps. You just need the sum as the answer.
You're right. Thanks. So it's taking a long time. Yeah, so the answer is it's pretty slow. I also had that clever idea at some point, but it's pretty slow because it's doing a lot of extra unnecessary calculation inside somehow. So you could do, for example, you could do rand, yeah, I don't know. I can't think on my feet. Okay, so as I say here, of course you can do these things in C or Fortran or whatever, but it's just going to be so painful. Well, not even that painful maybe, but I mean it's so easy in Julia, and you'd have to think quite hard to do it in C, right? Okay, how am I doing? So let's collect some data and look at it. So I'm going to just use a nice, so usually the default thing to create an array should be an array comprehension, in my opinion. I mean, if it's a nice simple array where you're just looping over the same thing n times, just use an array comprehension. And so I'm going to calculate the data, and now I'm going to use the histogram function from plots. And here's a histogram, and I can just change the number of bins. And we can see that there's this parity issue of random walks, that the simple random walk like I did can only reach even numbers, basically. And that's why I've got this weird business going on. But of course, when you change the number of bins, that effect goes away. And so often we might have an analytical result available for one particular case. And so in this case, we know that the result should be a normal distribution with a certain variance. And that variance is actually equal to the number of steps, it turns out. So let's use the distributions package, which is a very nice package that provides a world of statistical distributions, or probability distributions. And we can use Unicode characters in Julia. So here, I'm using mu, which I type as \mu. So I use LaTeX syntax, and I press tab, and it'll complete this mu to a nice Unicode symbol, mu. And I can do the same thing for sigma and the same thing for square root. So \square root, tab gives me the square root symbol. So I have 10,000 steps, so I need the square root of 10,000 as my standard deviation, sigma. And then what I'm going to do is draw my same histogram, and on top of it, I'm going to plot the PDF, which is the probability distribution, probability density function of this thing normal. So that's an object, a type, in the distributions package, which represents a normal distribution with a mean, zero, and variance sigma. And this is an anonymous function. So so what's an anonymous function? It's just a function that doesn't have a name. So it's the function which maps x to this thing. Okay, and let's have a look at that. So there it is. So indeed, the histogram didn't do such a bad job. I'm plotting it with some width of line. And so I can even fill the thing in. Except I probably won't remember how to do that. So there's a transparent fill. So alpha is transparency, right? So you can do some pretty neat things with this plots function and this plots package. So here I've added to the x-axis this distance thing. So now I have a nice plot that I want to include in my latest Nature paper. So I'm going to save that figure with the savefig command. So for example, to a PDF file, we should always use vector graphics when we can. So that's PDF and SVG, not PNG. And then I can use semicolon will send a command to the terminal, to the command line. So on Mac, there's this function, there's a command called open. So this is actually running a Mac command to open this PDF, and there it is, a nice PDF to include in my paper. Okay, so let's summarize this workflow bit. Basically, I want to calculate fast, and Julia can do that for me, but then the result of that fast calculation is immediately available to me, and I can just stick it straight into my interactive visualization, collect some data, do whatever I want with it. So this is just in one place. The notebook gives me this nice data analysis flow. It's just great. Questions? Yeah.
When you did your x-axis labeling,
yeah.
you said that. Why does that function use a bang?
Good question. So the question is, why does the x-axis bang function, why does it have a bang? And the answer is because I'm trying to add something to the pre-existing plot. So if I remove that x-axis, the bang from x-axis, well, I think that doesn't even exist. But suppose that I had this h line. Right, so that added a line at 0. Suppose I take out that bang, what's going to happen? The whole plot disappears. Why? Because it's just replacing the plot with a single horizontal line at 0. So I need that bang to add to the pre-existing plot. More questions?
So is it like a log list and these functions basically return some kind of log object and manipulate themselves?
So the question is, do these functions return some kind of plot object? And the answer is yes. So if I put, for example, P equals that, then I can ask, what is the type of that thing P? And it's this particular kind of object. And then I can, for example, just put P and it'll replot that thing, and then etc. Yeah, I can't tell you much about the internals, to be honest, but yeah, it's doing something like, yeah, it's manipulating objects in the end, yeah.
What was the -1:2:1 here?
Thanks. The question is, what was the -1:2:1 thing? So if I put R equals that, I can ask what is R, and it's something called a step range. So a range is this generator thing that generates a range. So this is something that basically the answer is something that goes from -1 to 1 with step 2. So so it's probably not very intuitive what that is. So I can actually ask Julia what it is with this collect function. So there's some discussion about whether collect is a good name. It just means go through this generator and collect all the things that are inside it and put those in an array. And so the answer is, what is inside this thing is -1 and 1. Okay.
Can I write my own generator?
What?
Can I write my own generator function?
The question was, can I write my own generator function? The answer is yes, but it has just changed how you do that in 0.6, and I won't be able to do it in this moment. So you use something called a channel, is that right? Do you know? Okay, we don't know. Good question. Okay, more questions? So just quickly, of course I want to be able to save the data as well. So how can I save the data? So there's data I just generated, right? So it's some kind of array. It's a vector with 10,000 elements. Suppose I want to save it to disk. So the simplest way is with this strangely named write DLM function. So DLM stands for delimited. So I can actually delimited is, the delimiter is what you use to separate the data. So I can separate them with commas or with returns or whatever. So I don't like the name, but it probably will go away in the future, this function, whatever. So but it's still the simplest way of writing the data. So I can just put a file name here and this data object, and it will write that out to the file, and then I can read it back in with read DLM. And so when I read it back in, here's the new data, right? And here's the old data. So the old data was a one-dimensional array of integers, and the new data is a two-dimensional matrix that has one column of floats. So it made a big mess. And of course, there are options to read DLM that I don't know that you can go and read about in the documentation to change that and read it back in as an integers instead or whatever. But I don't want to read all that stuff. So we're going to use a different method, but there's a question.
Microphone is on.
Oh. No, it's on. Is this one better? Is this one better? Oh. Ready. Can you hear me now? Oh. Should have said something. Okay, yeah, that's much better. Okay, yeah, so we're annoyed with this write DLM function, so let's do something much better. So you forget about write DLM, never use it. So we're going to use a nice package called JLD, Julia Data. So what does that do? So I've got my data and I've got some variable that I want to store called I. And so this is going to save all of these objects in this file with all the information about what kind of objects they are. In other words, their type. And this is the syntax. So I have save. I put the name of the file, which is going to end with .jld, the name of the variable, the sort of name that I want to associate the data with in the file. So final pause, data, the object, and then another one, another name, and another object. And when I load that back in, so that's going to save it in this special format called JLD, which is a Julia-specific format. When I load it back in, I get this strange result, which is a dictionary. So a dictionary is an associative array that associates to this name this object. So what is this JLD file? It's actually underneath, it's an HDF5 file, which is an industry standard format, hierarchical data format. And you can read this file with any random tool, except this extra information, which is the this type information. So when I read it back in, I get this dictionary, and I can extract each element of the dictionary, each object in the dictionary with this syntax. So it's syntax that looks like I'm accessing an array, but I put this string key in, and then it gets me back this variable with the correct type. And again, and I can do the same thing with final pos, or I can just load one piece of the file without loading the whole file in. So here I'm just loading the data that's associated with the name final pos inside the file, and I give it this name in Julia, and it creates an object with the correct type. Right? So JLD is the solution for storing data, as long as it's not a massive data. I mean, where massive means bigger than your hard disk or whatever. Okay. So finally, for this workflow thing, so we've now got quite a lot of code in this notebook, and it's spread throughout the notebook, and that starts to get annoying if you're coding a lot and changing a lot of things. So what I would now go and do is I would go through this notebook and sort of probably make a copy of this notebook first, then go through and remove all the bits of code and plonk them, put them in a Julia script. So for that, I'll use Juno. So here's Juno. So I'm going to make a new file, and I'll tell it that I'm using Julia, so it knows that it's Julia. And so what can I do? I can do things like x equals 3, and execute that with Shift-Enter, just like if it were in the notebook. And then x equals rand55, and execute that, and it will tell me what x is, and I can click on this thing and see x and scroll around and click on it again to hide it. So I can evaluate things inline inside this editor, right? But it is a text editor. If I highlight all of this and I copy it and paste it, it of course won't paste the output, it just pastes the input. So it really is a text editor, but it's a text editor with this sort of added bonus that I can evaluate things. I can also plot there. I mean, it's becoming a really complete integrated development environment. There's an interactive debugger that currently only works on Julia 0.5, but soon will work on Julia 0.6. Okay, so then I can save that as a .jl file. Right, so let's write a little function. So I'm just going to make sure I'm in the right directory. So so there's this hello.jl file. I'm going to open that with Atom. Here it is. So I'm going to make a little function hello, print line hello. I'm going to save that file as a .jl file. So that's a Julia script. And then I'll go back to my notebook. I'll check that I'm in the right directory where I just loaded the file. I can have a look at the directory to make sure that my file is in there. What is it? Hello.jl and my hello.lj that I created. And then I'm going to include that with this include command. And so I can just use tab completion again inside the notebook, and it will complete this file name. And what it's doing is reading that code as if I had just typed it straight into the notebook or into the terminal. And so now that hello function is available, and I can run it like that. So that's the simplest way to sort of encapsulate your code into a nice little script. And I can run that from the command line as a script as well. So if I'm on the command line and I put Julia hello.jl, it will run it, and it didn't print out the answer. That's quite strange. Oh yeah. I need to actually call the function inside the script, and then when I run it, sorry about the jumping, it does actually print out hello. Okay. Yeah.
So one of the things that slightly annoys me about Python is that you can't easily import a script from another directory without making it into a package. with the import command. In Julia, can you easily use relative and absolute path names?
So the question is, can I include a file from a different directory? And the answer is yes. So let's say, I don't know, whatever. Right, so this now says hello2. It's a different script in a different directory. And now I'm going to import that one instead. So I'll use the Unix syntax // and now it does hello2 instead. Now, this is just the simplest way that I could do this. So later on, what I should really do, which I'm not going to talk about, is make this into a module. So if I have several functions, I might want to make a random walks module. And so there, the point of a module is that I can control which functions are available from outside. So I have some kind of access control. I can't really control it, sorry. I can control which functions I export, which are easily available. Everything is always available, so everything's always public. But some are more visible and some are less visible. And then the final step would be, okay, now, everybody in the world needs to use random walks, so we'll make an actual Julia package called random walks, and that has to have a special structure, and it has to live in a special way, and then it's a bit harder to import it from somewhere else. So you have to use something called load path, that I'm not going to talk about. Okay, so any questions before I move on? So I'm doing pretty badly for time, so I'm going to go fast. So I'm just going to say a few things about arrays. A few things have changed recently. So let's make an array with this. I can use this explicit syntax, which gets pretty nasty for anything more than a 3x3 array. Pretty annoying to do by hand. So that's a 3x3 matrix. What's a matrix? It's an array with 2 dimensions, which in this case contains integers. So the type of that thing is this thing. So we'll see what the curly brackets mean in a minute. And I can extract a sub-piece of that matrix with this syntax. So I'm using these range objects that we've just been looking at, and to get a sub-piece. And so the question is, what happens if I change this sub-piece? So for example, I can use this square brackets with 1, 1 to access that particular 1, 1 element of this matrix. And then I can change that element. And so this sub-piece changed, but the original matrix didn't. So the original matrix did not change, even though I modified apparently the sub-piece. And so the answer is that this square brackets notation makes a copy of this sub-piece. So it makes a new array and copies over the values. So sometimes that's what you want, but often it isn't. So when you don't want that, when you actually want it to just be reference to the same data and be able to modify that data from this sub-piece, then we use something called a view. So now the syntax for that is view. So it used to be something else that I don't even remember, sub something. And so I use this slightly strange syntax. So it's a view of M, this object that I'm trying to take a sub-piece of, comma the range, comma the other range. Right, so you could think that's a slightly unnatural syntax. So in a minute we'll see a more natural syntax. So what is the type of that thing? Is this extremely frightening long type. Right? But we don't need to be frightened of it. So what is this type telling me? It's telling me, or it's telling Julia, everything that it needs to know to use this array. So it's an array, it's kind of array, right? So yeah. So that Julia has a type hierarchy. So this is a subtype of array, of abstract array. So I can ask Julia, is V something of type abstract array? And it is. So abstract array is some sort of high-level abstract concept, and then it has a whole tree of types underneath it. So I can look at the subtypes of that. So yeah, I haven't said what a type is yet, but I'll talk about that in a minute. So there are all kinds of things that look like an array, basically. That's the point. So these are things that, in some sense, behave like an array, like a generalized array, whatever that means, right? So it's almost defined by what these subtypes are, what that actually means. So it's some kind of array which has integers, it's two-dimensional, and then there's apparently redundant information here that's saying that it's a subtype of a two-dimensional array with integers. And it's a subtype with these two unit ranges, and I don't remember what that Boolean is at the end. So that's all this is saying. It just looks scary because it's just sort of it's too much information in one place. Okay, so I have this V object which looks the same, the output looks the same, but the type is what's giving away that it's different. So for example, So for example, if I just do show V, then I don't see all this type information, and so I don't actually know if it's what kind of subarray it is. But if I now modify this sub piece of the array, so this